In this video, we are going to continue looking at substituent effects in electrophilic aromatic substitution reactions. So remember, our EAS reaction looks like this, where we have an aromatic ring of some kind, and we are going to replace this hydrogen with some kind of electrophile on here. And depending on what these substituents are, we can have different types of resonance going on. We can have electron donating groups that add electron density into the ring. We can have electron withdrawing groups which remove electron density from the ring, and then halogens, which is what we are going to look at today. And halogens kind of have their own weird little effect going on. So remember, with electron donating groups, we are putting this electron density into the ring, so we end up with these lone pairs and negative charge in the ring. When we have an electron withdrawing group, it's going to end up with electrons removed from the ring, and we are going to end up with that positive charge. When we have halogens, we have two different effects going on. The first one is the inductive effect, which is electron withdrawing. So just like with the alkyl groups, which were actually electron donating, this is just done through inductive effects. But in this case, because the halogens are more electronegative than the carbon, this is actually going to pull electron density away. But now, say we have this attack that electrophile there, so that we end up with the electrophile bound, and then we will end up with a positive charge in the ring. And so that looks like this. So now we've added our electrophile right here, and now we have this positive charge over here. Well, this positive charge can actually be stabilized through resonance with the halogens. So we can have the electrons move down here to form that double bond, and now we've made what's called the halonium ion. And so this is actually going to stabilize this positive charge on that carbon. We could, of course, then have these continue moving around. So we could have those electrons move there, those go back up onto there, and so we then move this positive charge around the ring. But the one that's important here is this halonium ion, which, like I said, is stabilizing the positive charge on that carbon right there. And so this is the resonance effect. And we can see that this is electron donating in this case. So the halogen is donating electron density in order to stabilize the carbocation on the adjacent carbon right there. And just like before, we can look at the electron density here. So we saw with our electron withdrawing group, the electron density in the ring is less than what we see for the benzene here. And when we have the electron donating group, the electron density in the ring is more than when we have just the benzene. But now with the chlorobenzene in this case, so this is our halogenated, we see that there is slightly less electron density in the ring here than there is for our benzene right there. And so the halogen is acting as an electron withdrawing group, but because it can also do that resonance stabilization, it's actually going to make it into an ortho para-directing group. So what we see for the halogens, they are deactivating, but they are ortho para-directing. So the other two types of groups we've already looked at in the past two videos, we saw that there was the activating ortho para-directing, which are the electron donating groups, then the deactivating meta-directing, which are the electron withdrawing groups. Now with halogens, we're getting kind of a mixed bag here. Now we have deactivating, but it's going to be ortho and para-directing. So it's a little bit of both types going on here. Halogens, like I said, are deactivating groups, yet they are ortho para-directors. The halogens are electronegative, withdrawing electron density from a carbon atom through the sigma bond. So this is that inductive withdrawal, but the halogens have non-bonding electrons, which they can donate electron density through the pi bonding. This is the resonance donation. So again, we have the inductive effect here that's deactivating. We see that this is going to make a dipole pointing this way, and so it's actually pulling electron density away from the ring. But we have the resonance effect here, so we can have one of the electron pairs move down to form this double bond, and now we're ending up with electron density going into the ring. So what's going to happen is that this is going to, as I said, be deactivating, but it's going to be ortho and para-directing. So this is going to be more likely to put it onto the ortho carbons right here or onto the para carbon right here. You then may be wondering to yourself, isn't there also inductive effects with the oxygen and nitrogen? Oxygen is famously quite electronegative. Nitrogen is also quite electronegative. So don't these also have the inductive effects? Well, yes, they do. But in these cases, the resonance effect is stronger with the oxygen and nitrogen. So what's going on is that oxygen and nitrogen give more electron density than they take. So the oxygen and nitrogen Also, being closer in size to carbon can form more effective pi overlap with the adjacent carbon in the benzene ring. That's why they can have more of the electron donating rather than electron withdrawing effect. So again, we have our resonance effect here, our inductive effect here. Inductive effect in the halogens is going to make it electron withdrawing. The resonance effect is going to make it electron donating. But what we see here for the fluorine, we have good overlap of the p orbitals. But because fluorine is so incredibly electronegative, that is going to end up winning out for the fluorine. With the chlorine, bromine, and iodine, we have poor overlap with the carbon p orbitals. And one of the biggest reasons for that is because now we are going into the 3p, 4p, and 5p orbitals here. So the chlorine, bromine, and iodine are on the 3rd, 4th, and 5th rows of the periodic table. Therefore, the p orbital overlap decreases, and they deactivate the ring because of their electronegativity. So if we look at some data here, so we can see this for hydrogen and carbon at the top. All of these differences here are comparing everything to carbon. So what we see is that the electronegativity difference for nitrogen and oxygen are plus 0.49 and plus 0.89 there, whereas for something like fluorine, it's quite a bit different. So that's going to be the highest difference. Then for the iodine, it is the lowest difference right here. Then if we look at the atomic radius, now what we see again with fluorine, now it's the highest difference in the negative direction. So fluorine being smaller than carbon, then iodine is the biggest difference in the positive direction. And so that's going to be bigger than the carbon. Then I have here in purple, this is the chlorine. This one is the closest in size to the carbon. But the thing to really pay attention to here, as I said, is that we have the different p orbitals going on with the chlorine, bromine, and iodine. And so we're going to get less overlap there because it has to overlap with the 2p orbital of our carbon. Then if we look at the effect of this on the relative rates, we can look at this on the middle column here. This is the relative rate compared to benzene right here. And then we can look at it with the right column compared to the chlorobenzene over here. And so what we see is if we have this activator right here, so that's our inductive electron donating group, this is going to make it 27 times faster than benzene and 1350 times faster than the chlorobenzene. But then what we see here is we can get the relative rate in order like this because the iodine is going to be slightly faster than the chlorobenzene, the fluorine is slightly faster but not as fast as the iodine, and the bromine a little bit slower but still faster. Then we can see right here that is the chlorobenzene right there. And so we can see all 4 of the halogens make it slower than just benzene right here. And so the halogens do slow it down, but not to an enormous degree the way that something like a nitro group would. And then, as we said, these are going to be ortho para-directing, and we can see that with the stability of the sigma complex. So if an electrophile reacts at the ortho and para position, the positive charge of the sigma complex is shared by the carbon with the halogen. So what we see here with the ortho and the para attack, what we end up with is the halonium ion going on right here. So this is in particular with bromine, so it's a bromonium ion. So we get that with the ortho and the para attack. And so in those positions, we can actually stabilize that carbocation. Whereas if we're doing the meta attack, we do not get the stabilized carbocation from the bromonium ion. So we do not form any bromonium ion with the meta attack. And so it's going to be less stabilized. So the reaction at the meta position gives a sigma complex whose positive charge is not delocalized on the halogen-bearing carbon atom. Therefore, the meta intermediate is not stabilized by the halonium ion structure. So the following reaction illustrates the preference for ortho and para. So what we see, we have our chlorobenzene here. We are going to do this nitration reaction. We end up with 35% ortho, 64% para, and 1% of the meta. And so again, even though this is a deactivator, we are going to be ortho and para directing with it. And we can see that with the energy diagram here. Again, these are all going to be slower than just the benzene, but we see the ortho and para are more stabilized than the meta in the transition state. And so that's going to favor the ortho and para addition rather than the meta addition. But anyway, that was it for this video. Again, what we've seen now through this video and the previous two, we looked at the activating ortho para directors right here. Then in the previous video, we looked at the deactivating meta directors right here. Then in this video, we looked at the deactivating ortho para directors right here. In the next video, we'll look at what happens if we have more than one substituent. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.